Hello! In this video, we're going to prove the following theorem. Suppose f is a function from a to b, and f inverse is a function from b to a. Then, f inverse compose f is equal to the identity relation on a, and f compose f inverse is equal to the identity relation on b. Okay, so first of all, let's review what these compositions mean. To start, for f inverse compose f, we can think of B as our intermediate set, right? And we really have that f inverse compose f is a function from A to A. Now, for f compose f inverse, we can think of A as our intermediate set. And we really have that f compose f inverse is a function from B to B. Now, we know that the identity relation on A is a function from A to A, and the identity relation on B is a function from B to B. Okay, so really, there are two things we want to prove. Let's first prove that f inverse compose f is equal to the identity relation on A. Now to start, I would first like to note that both f inverse compose f and the identity relation on A are functions from A to A. So really, to prove that they're equal, what we can do is we can prove that for every element A in the set A, we have that f inverse compose f evaluated at A is equal to the identity relation on A evaluated at A. So to prove that they're equal, all we got to do is prove this statement. And we're trying to prove a statement about every element in A. So give me an arbitrary element of A. I'll call it A. Now, since A is an element of A, and f is a function from A to B, we know that f has a functional value at A. We could say, for instance, let B equal f of A. Now, this is equivalent to saying that A comma B is an element of f. And if you recall, by definition of the inverse of f, this is equivalent to if we swap the order of A and B and write that B comma A is an element of f inverse. And then, because f inverse is a function, we can write this as A equals f inverse of B. But also notice, we have that A is an element of A, and f inverse compose f is a function from A to A. So really, we know that f inverse compose f has a functional value at A. And if you recall from compositions of functions, we know that f inverse compose f of A is equivalent to f inverse of f of A. Okay, but we know that f of A is equal to B, so we can replace f of A with B. But f inverse of B is just equal to A. But also, we know that A is the identity relation on A evaluated at A. So, putting this together, we started with an arbitrary element A in A, and we deduced that this is equal to this. So really, since A was arbitrary, this means for every element A in A, this is equal to this, which means we've proven precisely this statement. In other words, we've proven that f inverse compose f is equal to the identity relation on A. And now we're going to prove that f compose f inverse is equal to the identity relation on B. And to do this, let's first note that f compose f inverse and the identity relation on B are both functions from B to B. So really, to prove that f compose f inverse is equal to the identity relation on B, what we're going to do is we're going to prove that for every element B in the set B, we have that f compose f inverse evaluated at B is equal to the identity relation on B evaluated at B. So to prove they're equal, we want to prove this statement. And so we're proving a statement about every element in B, so give me an arbitrary element in B. I'll call it B. Okay, Now, since B is an element of B, and F inverse is a function from B to A, we know that F inverse has a functional value at B. We could say, for instance, let A equal F inverse of B. Now, we know that this is equivalent to saying that B comma A is an element of F inverse. But another thing, if we recall from the definition of the inverse of F, this is equivalent to if we swap the order of B and A and write that A comma B is an element of F. But since F is a function, this is equivalent to if we write B equals F of A. Okay, and also, because B is an element of B, and F compose F inverse is a function from B to B, we know that F compose F inverse has a functional value at B. And then, from composition of functions, we know that F compose F inverse of B is the same thing as F of F inverse of B. Okay, but we know that F inverse of B is equal to A. So we can take F inverse of B and replace it with A. So we get F of A. But F of A is equal to B. And we know that B is the identity relation on B evaluated at B. So really, through this chain of equalities, we have established that F compose F inverse of B is equal to the identity relation on B of B. So really, we have proven this equality. And since B was arbitrary, this means for every element B in B, this is true. Right, so we've proven precisely this statement, which means we've proven that F compose F inverse is equal to the identity relation on B. And so this completes the proof. And yeah, that's pretty much how you could prove this theorem. And yeah, that's pretty much it for this video.